Let us start lecture 22. The course is phase diagrams in single component and binary systems. Today's topic will be on phase diagram in case of iron, and then we will try to analyze one important effect that is experienced in any moving object in water system, like impeller that pumps, water pumps, where we have blades. Those blades are attacked. Then we have propeller blades in case of ships. So, those blades are seriously affected by cavitation. There is a kind of damage that happens due to frequent bubble formation and bubble collapse. Okay? And that bubble formation and collapse, that also is dependent on that particular analysis part, how bubble forms and how bubble collapse, that can actually be explained with the help of water phase diagram. So, we will try to analyze that. In fact, we will also try to see why at high altitude water boils at a lower temperature, and that actually leads to the cooking is not proper at a high altitude. So, that is what one needs to use pressure cooker to cook, to boil rice. So, we will try to analyze that too also. If you see the topic, phase diagram in single component iron system and explanation of cavitation effect with water phase diagram. So, if I try to look at iron, so this phase diagram iron, in fact, there also we will be using the same principle, okay, where we will be using this equation dg equal to v dp minus s dt, as well as we will also be using dp dt equal to del h t del v. These two equations will be combined, coupled, and then to get the phase diagram. So, we will go to the phase diagram directly. See, if I try to see phase diagram, so if I try to do it here, let us say this is temperature and this is pressure. And remember, here I am just this is in degree centigrade, okay, and this is in log scale, because that pressure difference from solid to vapor, that range is quite a large range. So, that is what we are taking log, so that within a small section in the scale where we can actually put all the values. So, this is log P, and here it is in atmosphere. Okay. So, the plot is like this. It may not be true to its scale, but it looks like this. So, here we have okay. So, here we have vapor, here we have liquid, and in case of iron we have different crystal structures, pure iron. So, those are allotropes. We have alpha, then gamma, then delta. So, alpha has BCC or body centered cubic, gamma is FCC, face centered cubic, and delta again it is BCC, body centered cubic. So, there are other phases like beta phase is also there, but that appears at a different pressure and temperature. Within the pressure and temperature what we are considering, that time we will not experience that beta phase. If I try to look at a 0 here, so 0 suggests, since it is log, it suggests 1 atmosphere. Okay. So, there if I draw line. Okay. So, it will be cutting parallel to the temperature axis, it will be cutting at 4 points. 4 points. And those temperatures are, this one is 1 atmosphere 910 degrees Celsius, and this one is 1390 degrees Celsius. This is 1539 degrees Celsius, and here it is around 3057 degrees Celsius. And if I try to look at pressure at this point, around this point is close to around -10 log scale value. Okay. And like that way you can see different values. This is 2, rather -2, -4, -8, -6, -8, like that it would vary. And temperature, if you see, this is close to 1000 degree, and then we have this one is close to 1500. Since it is considered 3500, so you can put 3500. So, this is 3000, and so this will be 2500. This is around 2000. So, like that way the temperature varies. Now, if I try to see those lines, equilibrium lines, alpha, gamma, and interestingly, generally high temperature phase has a higher volume, molar volume, but typically in case of alpha gamma transformation, gamma has lower molar volume. So, for alpha gamma transformation, gamma is a high temperature phase. So, del H alpha gamma transformation is positive. Okay. Whereas, molar volume of gamma is lower than molar volume of alpha. So, then it basically is negative. So, if I try to look at dP dt del V, so this term becomes negative. So, the slope should be negative. So, that is what we see, a negative slope for alpha gamma transformation. But all the other cases, the high temperature phases have higher molar volume as well as higher enthalpy compared to the low temperature phase. Like gamma to delta, you see it has a positive slope, since delta has a higher molar volume as well as higher enthalpy compared to gamma. Also, if I try to see delta to liquid, liquid has a higher molar volume as well as higher enthalpy compared to delta, again this has a positive slope. Now, this we can actually reflect with respect to free energy temperature plot, because here I am fixing the temperature pressure. So, if pressure is fixed at 1 atmosphere, so then I should use free energy temperature plot to understand those equilibrium points at 1 atmosphere. So, if I try to corresponding points, if I try to project those points. So, let me project it here. So, this projection would be here, this projection would be on the temperature axis, this is G, pressure equal to 1 atmosphere, and this one would be here and this one is here. So, this is T liquid vapor, this is T delta liquid, this is T gamma delta, and this is T alpha gamma, and those are the equilibrium temperature at 1 atmosphere for the corresponding phase change or phase equilibrium. So, now I see that vapor phase, and also we can see that entropy of alpha should be less than entropy of gamma, less than entropy of delta, less than entropy of liquid, less than entropy of vapor. So, the vapor phase would have the maximum negative slope and alpha would have the lowest negative slope. So, now I can draw those lines. First is, if I draw BCC, so this is, let us say this is G alpha, then G gamma would be this one, it would extend, this green color is G gamma, then at this point, so at this point we see G alpha equal to G gamma. Then we have another one delta which appears, and delta has BCC and alpha has BCC structure. So, these two lines should actually merge, then this is merging and this line extend like this. So, this one is, if you see this line, this is G delta, and the liquid one would have crossed this point like this. Okay. In fact, I can draw this delta line with a different color. I can do it with red color. Okay. This is delta. So, here we have equal to G liquid, and when we come to liquid vapor equilibrium, I would have, this is GV and this point corresponds to GV equal to GL. So, I have, and we have to indicate one more point, which is this one, which is G gamma, is basically G gamma equal to G delta. So, everything is in place, and accordingly we see that how the hierarchy of equilibrium is decided, and we are getting different transformation points or equilibrium points with respect to free energy temperature plot at 1 atmosphere. So, that is the correlation between phase diagram of iron and its free energy temperature plot at constant pressure. Fine. So, and why I have shown this iron phase diagram, because you see here we have two solid state transformations, solid to solid, one is alpha gamma and then gamma delta. Those two equilibrium lines are actually having, one is having negative slope, one is having positive slope, depending on the molar volume difference of those phases. So, now coming to the other part which we want to discuss for today's lectures. So, we want to discuss the analysis of cavitation with reference to H2O phase diagram. Now, if I try to look at the cavitation part, cavitation is very dangerous to the system which is moving in water, and that time because of the rapid movement the bubble forms on the substrate, and that bubble, when it collapses, that time it lead to a shock wave on those substrate, and that shock wave could be a very, it can create a very high stress, and that stress can actually plastically deform the structure. Okay. And once deformed, that particular zone becomes highly active, and then the second thing that comes up is basically the electrochemical degradation, or we call it corrosion. Okay. So, dissolution goes up, dissolution rate goes up. So, the first thing is basically the bubble formation, and then bubble collapse. Second thing is bubble collapse, then third thing is shock wave, pressure creation or stress creation, plastically deforming the surface, and then subsequent corrosion. So, that way degradation proceeds, and at time it can be so serious that those moving objects in water system, liquid water mainly, liquid water system, they can actually break into pieces. So, like what are the moving objects? Like impeller blades, then we have propeller blades. So, those are important aspects of pump as well as ship movement. Why bubble form? Because it is in a system, water system, which is liquid. So, liquid is stable, but because of the rapid movement of those blades, there could be creation of low pressure, and that low pressure can actually change the equilibrium temperature for boiling. Okay. And then immediately once the boiling happens locally in water, so that will create a bubble. Okay. That bubble contains nothing but no air, bubble contains moisture, which is basically H2O vapor. Okay. So, how it happens, let us analyze that. So, if I try to look at the cavitation part, so what cavitation happens? For example, on a substrate, iron substrate, let us say a bubble forms, okay, and then we have water pressure on the bubble, and that water would create a kind of jet, compress this bubble, and finally it will implode actually, and water jet will hit this section and it can create shock waves. Okay. So, that way this particular zone is vulnerable for deformation, plastic deformation. So, now this is the bubble, which is water bubble or water vapor bubble. So, this is the event that happens, and this is nothing but cavitation. Now, when we try to look at the pump system, simple water pump system. So, water pump system, we have a discharge, and here we have blades, and this is a small I section, and then we have a suction zone. This is I, this is a schematic plot. Suction, you can look into internet and to check how the pump system works. So, this is at a temperature T, let us say, and at T stable water is basically liquid, stable phase is liquid phase, and then this, because of this blade movement, blade moves at a very rapid speed, it is basically it rotates very rapid speed, and that actually ejects the water, that actually sucks the water through the suction zone, through the air to the discharge zone, and then it goes out, and that way pump works. So, this high pressure, high speed rotation leads to a low pressure here, and here the pressure would be lowest P, and here again discharge, if you see, it goes to outside. So, you can say high pressure again. Okay. Now, if we try to look at phase diagram of water, this is temperature, this is pressure. So, this is my phase diagram, this is liquid, this is solid, this is vapor. Now, we are at temperature, let us say here, we are at temperature here. Okay. Now, that time my saturation vapor pressure is P1. Now, by chance, or let me just put this one little on the right side, so then it will be clear. So, let us say my temperature is here T1 and that time saturation vapor pressure is P1 and I am operating at 1 atmosphere, let us say. Okay. So, then to start with, that water would remain in the single phase zone, that is here. Temperature is not changing. Now, if pressure drops and let us say I have another pressure which is P2, let us say pressure drops to this point which is P1. So, then water and vapor would equilibrate, so that liquid water and vapor would coexist. But if you go farther down at P2, it will go to the vapor zone. So, the water would try to go to the stable vapor phase, and that if that happens locally, so surrounding it we have all water, liquid water, but locally the pressure drops to P2. So, vapor forms and that vapor should be accommodated in the form of the vapor bubble. In the subsequent step, again the pressure goes up, it comes to this level and then further goes up and it comes to this level. So, again I see, so it comes back to the original position 1 atmosphere, it becomes liquid. So, the vapor phase when it goes to liquid, it has to collapse. So, that sequence happens in case of impeller blade. Okay. And whenever bubble forms, that bubble forms more on the surface of the blade, because surface of the blade as well as the body of the pump, because those are actually providing heterogeneous nucleation sites. So, that is what there the possibility of formation of bubble will be more on those surfaces. So, this sequence happens in case of in these zone, the suction, I and discharge zone. So, if I try to plot the pressure distribution as a function of distance, pressure distribution. So, let us say this is suction zone, I am putting it as S and this is I put it as E and this is let us say D, discharge. Okay. So, I put it as D, this one is S and this one is E. Okay. So, if I see the pressure distribution, the pressure, let me put it on the left side, little left side, this axis. So, the pressure distribution would be like this, it will start decreasing, it will go to this and then again it will start increasing, and discharge we have higher pressure, that is what water is ejected at a high speed from the discharge. So, discharge zone we have this pressure. So, the line would be like this. Okay. And this is discharge and then it flattens out. Now, this is the pressure distribution from suction to discharge through I, and I has the lowest point. Now, my saturation vapor pressure at T1, let us say this is operating at T1, the temperature of the water. Saturation vapor pressure is T1, the P1. If I think if that P1 line is at this position, let us say this is my P1 line. Okay. So, that means beyond these particular points, liquid water would be stable, because that pressure would be in that pressure and temperature will take the liquid take the water into the stable liquid phase, and below those lines will take the liquid water into stable vapor phase. So, I would start forming bubble from this point, these points onwards bubble will form. Bubble will form. Now, bubble will continuously form in this zone, Now, from I onwards towards discharge, the pressure starts increasing. So, at this point bubble will collapse. Bubble will collapse and this particular effect will be observed, fine. And why bubble will collapse? Because this pressure point is at this point pressure is leaving P1 at T1 and going towards the positive pressure, and that would take the vapor into a stable phase which is liquid. So, bubble existence will be lost. So, when that thing repeatedly happens, because as we rotate that particular impeller blade, continuously this pressure line will be formed and continuously the bubble formation, bubble collapse, that will repeatedly happening, and it will give shock waves on the platform, the surface of the blade as well as surface of the body of the pump, and they will create deformation pressure and they will deform, and once it is deformed, that deformation can create some pits, small pits, and those pits can be acting as a stress raiser, and those pits also, because it is deformed, that means it is a high energy state, the solubility corrosion tendency goes up. So, this both the effects will combine hands and then aggressive degradation happens, and finally, there could be a situation that all those pit zone could be so deep that blade can break into pieces. So, that is why the cavitation damage is so dangerous, because if once the blade breaks, your efficiency of the pump reduces, okay? And that can be easily explained with this pressure, temperature, water phase diagram, okay? In fact, when we talk about propeller blade, so that propeller blade, when it is moving and it is going, so you will always have such situation of low pressure and high pressure, okay? Because when the blade rotates, so that actually leads to a low pressure zone and then again high pressure zone, and the low pressure zone creates, if the blade moves this way, if we try to see blade moves the forward direction, the backward direction will have a low pressure zone. So, the back of the blade will have cavitation more, okay? So, like that way that typical cavitation damage can be correlated with the water phase diagram. So, finally, one more point let me just explain. So, these lines, if I try to see these lines, this particular liquid vapor equilibrium line which talks about the boiling point. Now, if I am 1 atmosphere pressure, that boiling point is 100 degrees Celsius. So, 100 degrees Celsius boiling point at 1 atmosphere, fine. And let us say if I cook something, let us say I am cooking rice, I put the rice in water and then I heat it, the water boils at 100 degrees Celsius, and that time I could have lot of heat stored in the water at 100 degrees Celsius. Apart from when it boils, it will have its latent heat of boiling. So, all those heats will combine each other and cook the rice quickly as well as properly. But once we go to high altitude, pressure drops. See, pressure drops, so that means my boiling point would also go down along this liquid vapor equilibrium line. So, if I go to a high altitude area, so the pressure drops, my boiling point reduces. So, I have less heat to cook the rice. So, the rice will not be cooked quickly. So, that is what at high altitude one should use pressure cooker, because the pressure cooker artificially increases the pressure and that actually increases the boiling point of water and it allows a better cooking. Okay. So, that is another example of this water phase diagram. Explanation of that event can be done through water phase diagram. So, now we have understood water phase diagram, CO2 phase diagram as well as iron phase diagram, and we have, and in fact, if you see, all depends on the phase equilibria. So, that is what we have talked to a great extent on the equilibrium aspects, when we would reach equilibrium, okay, which is basically minimization of free energy, fine. And on that way we experience the equilibria between different phases, and then finally we come across this phase diagram. So, now we have done single component. So, next class onwards we will start going into binary phase diagram, and that time we have to bring in chemical potential, because in case of single component composition is fixed. So, that is what we did not consider chemical potential, but once we go to binary or multi component system, we have to bring in composition effect. Okay. So, till then we will end today's lecture. Thank you very much.